Okay, so my intention today then is to go over the our hands-on problem 6. So let's go ahead and dig into that. Okay, so reminder of what we're doing then. We're going to be looking at pulmonary exacerbations, and in this case we may have well, if you recall before, we looked at the time to the first pulmonary exacerbation. Now we're going to consider the time to not only the first, but also the times between subsequent exacerbations, so that we can actually model all of the occurrences. And in our case, we're going to assume a constant hazard as part of our model. So we're going to start here. We've got our, as I said, working with the same data we did back in our first hands-on example, but we're going to extend the time frame so we actually get enough multiple events to make the modeling worthwhile. It was a phase 2 dose finding trial, parallel, 100 per arm, and some different dose levels here: placebo 20, 40, and 60 milligrams per day over 52 weeks. And we're going to look at those times of pulmonary exacerbation. So your mission here then was to model those. And just again looking at our exploratory data analysis on this, just looking at Kaplan-Meier curves for our inter-event time. So again, we're looking at the time to the first event and then the time between events in here. And this, so you're looking at then the fraction of patients with no exacerbation. Now, actually, this isn't quite explicitly true. It's actually, I guess you could call it whatever. It's really more the fraction of patients with no exacerbation since the last one. So it's probably need to find a better wording on that. But you can see from this, then you've got your survival curve, or again, it's 1 minus the cumulative distribution function for our time to event here. And we can see for our placebo group here, we've got the highest rate of exacerbations occurring. And then as we you can see that at least roughly we've got a dose response going from 20, 40 to 60 milligrams, looking at the overall incidence. And then the two curves on the right are breaking it out for between the patients who were receiving no chronic antibiotics versus those who were in here. So the model I had proposed that we explore is the one you see here. We've got our time to exacerbation is going to be described by an exponential distribution, which is equivalent to saying a constant hazard, or actually it's constant within an individual. And the hazard for the jth individual here is the product of some baseline value here. I guess you'd call it baseline or placebo hazard function here, times what I label as E drug, which is then a modifier on that due to drug treatment. And our baseline here, we're allowing the possibility of inter-individual variation on our H0 value. So again, it's log normal. And then the mean here, this log H0 hat, we're just using a sort of a linear regression function for that. So we've got our intercept, a term due to the baseline FEV1, and another term due to chronic antibiotic use. This I sub-antibiotic just being an indicator, so it's 0 if they're not receiving chronic antibiotics and 1 otherwise. And then the E drug component is an Emax, or I say an Emax model. I guess it's an inhibitory Emax model. And just a reminder, this FEV1J here is actually not a model parameter. It's the observed baseline FEV1 for that individual. and then pretty weakly informative priors for everything here. Closest thing to an informative element, I would say, would be the Emax here. We've restricted between 0 and 1, which is, I suppose, since we're assuming it's inhibitory Emax, so I suppose the one thing we're assuming here is that the drug is not going to make it worse. So in that sense, it is informative. Okay, so let's see. Okay, so let's take a look at what an implementation of this thing looks like in BUGS. And let's open that up here. So in our hands-on 6, let's pull up the model. So that's just the hands-on 6.txt. Okay, let's make it bigger here. Now, okay, actually while we're at it, why don't we go ahead and open up the R script too that goes with it. Okay, and just a reminder on the data set too. Let me go ahead and fire that up. There it is. Okay, so the data set we're going to start with is we've got a patient identifier, we've got dose, baseline FEV1, an indicator for whether or not they're getting chronic antibiotics. I've also got it for their rhDNase and age, but we're not going to be using that in our model right now. Then we've got this T exas, so that's going to be the time of the exacerbation. And the way this is written is this would be the time at which an exacerbation occurred, where it's elapsed time from the beginning of the trial. And it's in weeks in here. And then finally we have an indicator at the end which indicates whether that time that's listed in the T-exact column is actually an exacerbation event or is it a censoring event. So for example, here we can see for our first subject here, our first patient, they've actually only got one record. It's actually a censored record and it occurs at 49 weeks. So that means the last time we knew anything about that patient was at 49 weeks from the start, and at that point they had not experienced an exacerbation. Whereas if we look at subject number 2, what we have is we can see we've got 2 non-censoring events. In other words, those are exacerbation events and then a censoring event. So we can see at 18 weeks and at 20.4 weeks that patient had an exacerbation event, and then at 52 weeks the study was over with no additional exacerbation events. So all of those will represent relevant data when we pass this on to our modeling. Now what we're actually going to do, and I'll show you that in the R script, is when we structure the data, we're going to structure the data in terms of sort of the time between events. So if we consider the start of the study our first event, then you'll have a value that'll go from 0 to whatever the first event is, whether it be a censoring event or an exacerbation event. And if there are subsequent events, we're going to pass the time since the last event. So right now the data, as you can see for our subject 2, you can see is the absolute time relative to the start of the study. We're actually going to recalculate values then that we're going to pass to BUGS. So what we're actually going to pass to BUGS, for example, is the first value is going to be 18. The next value will be the difference between 20.43 and 18, so it'll be like 2.43, weeks for the time to the next event, and then finally the time to the very last event, in this case a censoring event, will be the difference between 52 and 20.43. So that's how we're actually going to set up the data that we're going to pass to WinBUGS. And in fact, maybe we'll start there, show how the data is structured. All the usual stuff at the beginning here, we won't even go over that. Let's go right to the data. So we'll pull in the data set we were just looking at. So that's what's going on in this line. We'll skip the exploratory plots for the moment. Oh, actually there is one important item that I think I buried in the exploratory plots and probably should have put elsewhere. I'm calculating this t start value. In fact, now I got to remind myself what I did here. Yeah, I should have looked at this before I started class here because I'm trying to remember how I set this up. Okay, so we start out, we calculate t start as we take. Okay, so t start is taking the value that's in t exact. So for example, let's take our patient 2 as our example here. So okay, so there's our 3 values for t exact here. So the first line here in t start is going to create a new vector that is going to take the first 2 values in here, because you can see I've got this minus n row. That's by saying t exact minus n row, the number of rows in this, is I'm actually shifting. Oh, actually I'm doing that for the whole thing. So I'm shifting the whole thing by 1, if you like. I'm basically sticking one new record in, or one new value in the vector, and deleting the very last one. And then the next step here is, okay. The next bit here is just a trick to take care of the fact that I've got breaks between subjects. Maybe the best thing I can do is tell you what that amounts to for the individual subjects. So for example, for our subject 2 here, what's going to happen is this t start is going to be that you'll end up with 3 values, and in this case those 3 values will be for the first, for corresponding to this 18, the t start will be 0. For the next one it's going to be 18, and for the last one it'll be 20.43. So it's going to create basically another column, if you like, called t start, which is going to be the beginning of the interval for each one of these events. Okay, and then let's go down to the rest of the data stuff here. This next one here is just making sure that the patient identifier is an integer sequence starting from 1. Then I go here and let's see, I'm eliminating. Okay, now I got to remember what I'm doing. Oh, okay, I'm creating another data frame that consists of only the first record for each one of the patients. The only reason I'm going to do this is because I'm going to create some elements here that I'm only going to pass 1 value per individual, and that's going to be for some of the independent variables, some of the covariates. So that's all, the only thing that's going on here. And the second line here is just making sure everything's ordered by the patient ID. And then what gets passed goes on here. So we're going to pull off the number of observations that we have total, the number of patients. You can see that corresponds to the number of rows in this new data frame we made. Then we pass our patient identifier, the dose, and notice now I'm going to pass some of these covariates only as 1 value per patient. So you can see here this dose is coming from that second data frame where there's only 1 record per individual. Same thing is true for our baseline FEV1, for our indicator for whether they're in antibiotic treatment. But then for the times we have here, those I'll pass 1 value for each record in the original data frame. So here we've got for our time, our event time, which is either going to be an exacerbation or a censoring event. And you can see it says if it's not censored, the value that's going to get passed is going to be the difference between the t-exact value and t-start. So that's where I'm calculating the inter-event durations. And in the case where it is censored, it's going to put in a missing value. And then for the censoring, for our t-sensor value here, I've done something like I've done before. Actually, again, for this one, I've made it overly complicated. I could have actually just passed what's on the right-hand side. So this difference between the t-exact value and the t-start, and it's actually only going to play a role in the cases where the data is actually censored. However, the way I've written it is if it's I've got it so that if it's not censored, I'm putting in a 0. But again, that's actually an unnecessary extra step in here. Okay, and I'll explain what NSIM is in a minute after I show you what we're doing in the excuse me, what we're doing in the bug script. Okay, so that's our core that's the data structure we're passing in. Let's go ahead and now look at the bugs model. Okay, so we've got our usual, everything's in a model block. I'm going to have a loop here that's going to go over patients in here, and that's actually where I'm going to take care of most of the business in here. So we've got I is going from 1 to our number of patients. So the whole objective within this loop is basically to calculate the value of the hazard for the ith patient in here. And recall, let's sort of pull this guy up, recall that we described that hazard as the product of our H sub 0 times our E drug. So this first line right here is doing exactly that. The next couple lines in here, I guess it goes, yeah, the next couple lines in here are getting that value of H sub 0 for an individual. And recall over here, I've got it set up so that, I guess I can't highlight it that way, but our H0 value has some inter-individual variability, and it's described by a log normal distribution, and that's the same thing that's going on here, where I've got the log of H0 is normally distributed with some mean and some value for the precision in here. The next step is just converting that from the log of H0 to H0 itself, since that's what we're going to be using in that statement above. But then the way we're going to incorporate our various covariates into this is, except for the drug effect itself, is going to be through this log H0 component here, and that's described right here. So I've got a linear regression model for our log H0 mean. So that's equivalent now to this step right here in our equations. So we've got our log of H0 mean is going to be our intercept beta 0 plus a parameter beta FEV1 multiplying the centered representation of our baseline FEV1. That's why it's FEV1 baseline minus 70. And then our coefficient for our antibiotic, beta antibio, times our indicator for whether or not the patient is on antibiotics. So that takes care of that. And finally, for our drug effect, it's just our Emax model, our inhibitory Emax model here. So that looks again pretty much just like what we have over on our algebraic equations over here. So that's sort of the core of our model, for the core of the process for calculating our hazard, our individual specific hazard. And then I have a separate loop down here which is outside of that loop over patients, where I'm now looping where I is going from 1 to the total number of observations. And here we've got good old our t exact here is distributed exponentially with some hazard. Notice again I've used the our nested indexing here, and this patient I value then comes from our data set. So I'm pulling off the appropriate value for our hazard that was calculated in that previous loop. And finally we have our I function here in order to deal with our right censoring. Okay, so the combination then of these lines in the loop over patients, and this line then takes care of our likelihood function for our exacerbation times, as well as taking care of our right censoring. Then down here we have our various priors, and if you look through those you'll see they should match what I specified at the end of the page here in our slides here. So I don't think there's any particular surprises in that. So that's really the core of our model. Notice again that this model really doesn't look, the model itself doesn't look really any different than if we were modeling the time to the first event. And in fact, I could use this code as is if I only modeled the time to first event. In that particular case, n obs and n patients would be the same, so it would have been unnecessary to have two separate loops. But otherwise, it's the code is pretty much identical to what would be needed for that. So the core difference here is really in the data set, and this is very much like the situation where we were trying to deal with our piecewise constant hazard function. We used essentially the same trick there by treating each one of those intervals as kind of a separate event. And it's pretty much the same deal here. Now there are some assumptions underlying this that I don't think we really talked too much about. This is assuming that that having an event does not somehow affect the hazard for the next event. So the hazard remains constant throughout for any given individual under this model. Let's see. So what else do I need to tell you about this? So we covered the core of our model. Now there's a couple other bits that are going on here. One is we've got two kinds of posterior predictions in here that we're going to deal with. So we're going to do sort of a individual prediction and a population prediction. For doing the population prediction, I have to simulate the individual specific values of the H0 parameter here. So that's why you see this separate calculation of a new H-pred for doing the population predictions in here. For doing the posterior predictions specific for each individual, in other words, the individual specific predictions, you don't need a separate H-pred. We can just use the same H but do a simulated value as part of it. Now the one complication in this, let's see, I got a question here. How should I test the assumption that the hazard is constant for each subject diagnostic-wise? I don't have a good answer for you when you have fairly sparse information like we actually have here, and we'll see that has other consequences when we we'll look at the results here. I think I commented before that it's difficult to distinguish between, well, actually, let me step over here. Let's say we've got, we look at something like a Kaplan-Meier curve. Now, we can certainly look at a Kaplan-Meier curve and say whether or not it is consistent with a constant hazard, but constant in the sense that it's both the same within and between subjects, because what you're looking at here is sort of an overall distribution that accounts for both how things vary with time within individuals, but also how they vary among individuals for reasons that may be unrelated to time. But assuming that it is constant in both senses of that, you could say, okay, is this consistent with an exponential distribution, and which is basically saying if I was to plot this as a semi-log on a semi-log scale, are these things straight lines in that sense. However, if it deviates from that, I don't know whether that's because within each one of these individuals there's some time dependency on the hazard, or if it's just a consequence of a distribution of different hazards across individuals. So about the only time you can answer the question as you've posed it, whether it's constant within each subject, is you would have to have a number of events within each subject, enough events within each subject to really discern that. Beyond that, I don't know of any very clear diagnostics for making that assessment. Let's see. Okay. I know where I was about to go here. Now, normally when we want to do the posterior predictions, I would just go in here, and within this loop going over our observations, I'd just go ahead and generate, I would just, for each one of the observations, I would also generate a prediction. In this particular instance, that doesn't quite make sense to do it that way, because you've got a situation where the number of events that had occurred in the real data and the number of events that you should be simulating are not necessarily the same thing. What you really want to do is, in a sense, what you want to simulate is both the number of events and the times between them. And there would be various approaches we could use for doing the appropriate simulations for that. And if I was doing this in R, I'd probably do it a little bit differently than I'm going to do it inside WinBUGS. But you would kind of almost have to have a something like the equivalent of a while loop in here, where you would simulate the next event within an individual, and if that event occurs within the study duration, then you would keep that value, and then you would simulate the next event, and you would do that until one of the events falls outside the duration of the study. That's easy to do in something like R. That's not so easy to do within WinBUGS, which doesn't have a while type structure in it. You're basically stuck with a for loop type structure. So the trick I've used to do it inside of WinBUGS here is to specify a value of nsim, which is going to be the number of events I'm going to simulate for each individual, and I pick a value of nsim that I know is probably going to be larger, than the number of events that will really fit within the study duration, and then after I pass it on to R, I'll weed out any values that fall outside the observation period. So that's where, if we go back to our R script, you can see I put this nsim equals 5, and given the hazard that we're working with here, it's unlikely that an individual will have more than 5 exacerbation events within the study. So that's why I set the value at 5. If I found that wasn't enough, then I just set it bigger in here. So this is actually going to then simulate 5 events for each individual, and then after we pass those values to R, we'll weed out the ones again that fall outside outside the study duration. So, and that's occurring within this loop going over patients. So within the loop going over patients, we're going to do 5 individual predictions, and we're going to do 5 population predictions. Okay, let's step back to our R script and see what's going on in there. I sort of, well, let me keep on going here. Let's go down. You can see where I provided the initial estimates here. I don't know if there's a whole lot to say about them. I'm trying to remember where I dreamed up the values on some of these. I can't remember off the top of my head whether I used the values that I had originally used to simulate the data or whether I eyeballed them off the graph. There's some of them you could eyeball, some of them not so much. It would be difficult to come up, just eyeball it for I think most of these coefficients here. So I probably used the values that I had originally simulated it with, but I can't promise. I think if I was doing this with real data, I would probably use something like the built-in survival analysis functions within the survival package within R to do some initial crude fits and come up with initial estimates based on those. Let's see, so we got our specifying the parameters we want to keep and so on. The initial run, I just did the good old 3 chains, 10,000 per chain, 4,000 burn-in per chain as part of it, and so we run that. Let's see, what do I want to show? We'll go past the boilerplate here. So I realize I hadn't gone back over this to see how I did some of this. Okay, prediction of future observations. I may actually have to come back and revisit this. I should have reviewed this before class today. It's been a while since I looked in detail at how I had done this. Okay, the first part is getting the observed value using the built-in survival functions to build the Kaplan-Meier curve for that. And what am I doing for the rest? Oh, actually the rest of it is the same as what I had done back when we were looking at the multiple time to event, so I'm not going to step through that again. If you spot something that you actually want to ask about later on, certainly feel free to post it on one of the forums. And I think, yeah, I do the same thing over again for the individual, or for both the individuals and the population predictions. I'm trying to remember where I took care of the, where I took care of weeding out the excess simulated values here. Actually not spotting it off the top of my head. Oh, it keeps on bouncing back. Why does it do that? Yeah, I may have to revisit this to remind myself what the heck I did on some of this, because I should have had a spot in here where I was weeding out the excess predicted values, and I'm not spotting that off the top of my head. Okay, maybe I'll take a look at that and send you a note so that after I remind myself exactly how I did that. Because at the moment it just looks like I was keeping all of them. Maybe I did. Maybe I just kept the whole lot. Anyway, let me show you what the outcome was on this. Let's go ahead and go back to our files. It actually doesn't, the runs on this with 10,000 iterations aren't too bad. I forget the exact duration, but I seem to recall it was on the order of somewhere between 5 and 10 minutes to run one of these. But you don't need to stare at it with me while we do run them. So let's go to the results, our hands-on 6 value here, and let's go ahead and open up the plots. Come on, there we go. Okay, the first thing I see here is it's not looking too good. We don't have like, you know, really bad lack of convergence in the sense of the chains going to completely different places, but we've certainly got very extreme autocorrelation, and almost all of the regression parameters you see are beta 0, beta antibio, beta FEV1. Those are pretty extreme autocorrelations in here. Emax and ED50 are kind of doing a few funny things here too. Though the, you know, here it's the autocorrelation pattern is a bit different. It isn't the sort of wiggly snake thing you see with the others, but there's still things that obviously are kind of pathological there. And one in particular that's looking pretty bad here is this sigma H0. So that's the standard deviation for the inter-individual variability in our baseline hazard. So the first thing I can say is I'm not going to accept the results from this, given what we see there. You see that if we take a look at the, go ahead and open up the parameter estimates here. Is if we look at our effective N over here, again, that reiterates what we're looking at. You can see we've got some things like our, you know, our sigma H0 value. We've got an effective N of 29, which pretty much says we know almost nothing about that parameter, about the posterior distribution of that parameter. So we've got some problems there. Now, again, as usual, there's more than one way to resolve them. The one approach, of course, is brute force. I could just do lots and lots of iterations on this to try and get these effective N's up into the neighborhood of, you know, several hundred or 1,000 or so. But to do that, you can see for sigma H0, yeah, that's going to take what? That's going to take around, well, what are we going to take? It's going to take around 30 times as many iterations to get us there. So instead of doing our, you know, our 3 chains of 10,000, maybe we need to do something like, you know, 3 chains of 300,000, which is going to take a little while. So that's one approach. The other thing would be to look at some possible alternatives. One that I explored, for example, is, let's go ahead and close this. And I'll go ahead and close that. One was the approach that I used before with, what was that, in hands-on 5, is I tried, well, what happens if I do the truncated Emax, for example. So let's go ahead and take a quick look at the, actually before I open it up, let's take a look at the model. Okay, so the model looks identical, except down here is the parameters that I'm actually specifying priors on, instead of being Emax and ED50, is this E star and B functions. I've specified it a D star in the data set, and in this case I specified it as the highest dose we're working with, which was 60. So from that I can then calculate the corresponding Emax and ED50, and when I use this approach, what we end up with is something that looks like okay, well, what it looks like. Well, it's a little hard to tell exactly what's going on with Emax and ED50. You can sort of see, because they throw some occasional rather extreme values at us here. So I'd actually have to blow them up to see them a little bit better. The E star suggests that it's still not ideal, but probably better. Same thing with B. is they're approaching fuzzy caterpillar status, but we've still got some pretty significant long-term autocorrelation going on, at least in the E star, and the other coefficients here are beta 0 or beta antibio. And let's bring this up here, and our beta FEV1 still are looking pretty bad, and finally our sigma H0 looks about the same as it did before. So simply trying to deal with Emax and ED50 didn't help us a whole lot, and actually if I had really thought about it before jumping into that right away and looked at what we had back here with the original parameterization, I would have realized that, hey, Emax and ED50, though not pretty, are probably not our biggest problem. In fact, our biggest problem is probably that the number of multiple events that we have within individuals is probably too low to reliably estimate the inter-individual variability in the hazard. At least that's my guess on this. So one of the things you might want to do to explore that would be, okay, what happens if I just model this assuming no inter-individual variability, and that was the next step that I took in here. Let's go ahead and pull that up. So that one I've just called it hands-on 6 no RE. Here, let's pull in the model. Where do we go? And the main change that happens here is you'll notice that there's no component in here where log H0 is normally distributed. So I've now redone the model where I've just basically removed that line where we generate the our baseline hazard from a normal distribution any longer. There's no random inter-individual variability in this, and that's really about the only difference, plus removing the prior on the standard deviation for the inter-individual variability. So that's really about the only difference. And when we run that model, let's pull that up. Things behave fairly reasonably at this point. The ideal number of iterations is probably a little more, but you can see things are starting to approach fuzzy caterpillar stage in here. Let's see, got another question. Let me see what we got. Okay, the question is why would the number of events per each subject affect the inter-individual variability estimation? Well, for one thing, when you're dealing, let's start out with the extreme case of one event per individual. And in fact, it gets complicated because we've got some censoring case, but let's ignore that. Let's say one event per individual. When you look at the variability of any single event, so you've got basically you've got one observation per individual. So when you look at the distribution of those events, that distribution is a function both of how that, how the event is distributed over time within an individual, but it's also influenced by how the hazard for that event is differing across individuals. And simply by looking at a single event, there's no way to tell there's no way to decompose those two sources of variation. So with one event, that's the same problem you run into if you were to say to do a pharmacokinetic study. Let's say you do sort of the classic type of pharmacokinetic study that's often done in animals, where you sacrifice an animal and you only get one observation time for that animal. When you do that, there's no way to decompose the variation within and between animals. Same thing here when you've only got one event time. it requires multiple observations for an individual in order to be able to decompose those two elements of variability in this. And when you only have a small number of events per individual, it's, you know, again, it's harder to do that reliably. In our case, we have some individuals well, we've got a range of numbers of events across these individuals. Some patients have no events, some have one, some have two, and so on in here. So it's, you know, so we've got, and in general, it's a fairly small number. I actually should have probably gotten you a little statistic. Actually, we could probably do that. Let's see, what could we do here? Trying to think of a way to do it real quick on the run. I actually have to run part of this to do that. Maybe I'll hold off and see how much time we have as we're going here. But I could do a quick tally here on, you know, how many patients have no events, how many have one, and so on. But in general, you'll find it's a fairly small number of patients that have that have more than one event, and certainly, you know, and even fewer that have more than two events in here. Let's see. Hopefully I've addressed that question. So where was I going here? I was about to fire this up. Or I did already fire it up. Where is it? It's on ORE. Okay, so we're looking at this. We've got things that are at least close to fuzzy caterpillar status. Maybe for something like this beta antibio, beta 0, yeah, I probably want a few more. So I would probably do anywhere from 2 to 10 times as many samples to increase my precision on those. You know, beta FEV1 again is looking reasonably good, so they're fairly well characterized. In here, you can look at the posterior marginal distributions here. One thing that sticks out a bit is this B. Recall that B is the ratio of our D star, in this case 60, divided by ED50. Do I do the ED52? Yeah, I do the ED52 down here. It's a little harder to see the equivalent of this. What's happened here is, recall that for B, I actually didn't show that. For B, actually I'll show you right here, I used a prior that goes from, it's a uniform that goes from 0.1 to 100. In here, the 0.1 was to avoid the equivalent of ED50 going to infinity, which sometimes happens when you have limited information about the ED50 in here. What I end up getting back is something that looks like a mix of values that are more or less the same as the prior, which is a uniform going from roughly 0 to 100, plus some excess values that are down here close to the bottom on this. So B is not very well estimated in here. ED50, which is sort of inversely related to that, you can see you've got a bunch of values here down at the bottom, and then you've got a fairly long tail off to the right. And again, ED50 is not particularly well determined. On the other hand, E star, which represents the effect at a dose of 60, is moderately well characterized here. Emax, on the other hand, which is a function of both E star and our B here, again has this kind of long tail associated with it. If we look at the predictions, now in this case, I made plots both for the individual and population predictions, but because we have no inter-individual variation, they're identical. So we really only have the one set of predictions here. You can see overall it looks fairly reasonable, with maybe a little something off on the 20 milligram dose, but the others are looking pretty clean in this case. What else did I want to, oh, I know what else I wanted to comment on as we were talking about this. Now, the problem here, of course, is, again, I've said, okay, let's try a model with no inter-individual variation. Now, that's not because I don't think there is any. It's more because it looks like I don't have enough information to separate out the relative roles of inter-individual variation and residual variation here. Another thing that could be contributing to it is maybe I've got too complicated a model for describing, sorry, I'm bouncing around too much there, for describing our covariates in this. So, you know, maybe I really don't have enough information to get a solid estimate of something like, you know, the beta antibio and the beta FEV1. Now, having said that, though, the marginal posteriors on those two don't look that bad in here, so I'm not sure I want to believe that that's the core problem here. I think the core problem is that I really can't tease out the inter-individual variation, at least not after I also incorporate these covariates. I suppose if I wanted to make a little further exploration on this, I might say, okay, let's leave in the random inter-individual variation and see what happens if I remove a couple of these, if I remove a couple of those covariates, and try to account for it entirely with the random inter-individual variation and see what happens. You know, so let's see. Trying to think if there's any further to take this. Now, actually, let me catch my breath and see if there's any other questions that come up. Actually, while I'm waiting to see if something pops up here, why don't I actually take a quick peek at the number of observations that we do have per individual. I think I can do that fairly quickly. Doing extemporaneous programming in front of people always has its risks here. I'm just going to do is pull in the data here, and whoops, already I make a mistake. There we go. Okay, let's just pull in the data here. Okay, let's see. So what I'm going to do is, let's see, let's just do oh, let's see, which one shall I pick? That one. No, actually, that's not what I want to do. I could pick any one of these actually. Okay, what do I want? Patient. I think this will do what I want it to do. Okay, it does more or less, except let's capture that in an object here. Perfectly non-descriptive name here, and let's do. Oh, what would be a good thing to do here? I think. Yeah, okay, so here we go. So what I've just done here is I wanted to get some idea of the number of events, and actually the real number, this includes the includes the censoring events. Actually, I can make this fairly, if I just actually I'll just subtract 1, because I think every patient here has, okay, why didn't that work? I guess, oh, the table object doesn't work that way. Okay, actually these, what you see here is a count. It says there's, you can see there's 1 event in 232 patients, then 104 patients have 2 events, 44 have 3, 12 have 4, and we got 1 each at 5 and 6. Now keep in mind that every patient here has a terminal censoring event in here. So actually what you have is 232 patients have 0 exacerbation events, and 104 have 1 exacerbation event. So you actually only have what here, 44, 56, 58 patients that have multiple exacerbation events in here out of our total patient count of, what do we have, 400 patients? So that gives you some idea that that we really have a relatively sparse collection of information for characterizing the inter-individual variability, and that's probably the reason why we're having so much trouble characterizing that standard deviation. Okay, that's pretty much all I've got here, I think. Now we've got, next week we'll be off because of the Thanksgiving holiday in the U.S., so won't be doing anything then. Actually, I'm going to be, as I had queried you before about a couple additional topics, I'll be taking some time over that period to put together some material on that, since I don't have any prepared information on those. It looked like of those people who replied, everybody seemed to like the idea of looking at the hidden Markov models, so I'll come up with something. What I'll probably do is use the model that that the Monolix and Upsala group put together, looking at seizure counts, so I'll probably make use of that information. Now the second one was less clear. I've got a tie between doing time to event with a continuously varying hazard, or doing something where it's a combination of time to event and event magnitude in here. I guess if I don't see anything to break the tie, I'll probably sort of decide on the fly here as I start looking for material that I can use to cover it, since in neither of the case do I have at hand examples that I can just grab and give to you, so I'll actually have to construct those. So I'll see what makes sense as I go. So I guess I'll make a promise for something with the hidden Markov model, and then I'll choose between one of the others depending upon what kind of material I can pull together. And I guess if there's no more questions, I'll be signing off in a moment here then. Okay, doesn't look like there's any cropping up here. Oh, we got one more. Okay. Oh, I got a nice. Yeah, I guess the same to all of you too. For all of you, have a good holiday, and I'll talk to you. I guess it's in about a week and a half. So for those of you that celebrated here, enjoy a turkey or what have you, and I'll see you then. Bye.